Hello everyone, you're welcome to my second video on Python for chemical engineers. In the first video, we started by discussing optimization problem. We looked at a couple of optimization problems, so I will continue with the last problem on the optimization problem from the previous video. So here we're looking at the boiler turbo generator system optimization. I would crave your indulgence to read through this so that I can explain exactly how this problem is being formulated and also how we solve the problem, okay, using Python. So a steam and power plant for a small powerhouse fired by wood pump. To produce electric power, this system contains two turbo generators whose characteristics are listed in Table 1. Turbine 1 is a double extraction turbine with two intermediate streams living at 195 and 62 psi. The final stage produces a condensate that is used as boiler feed water. Turbine 2 is a single extraction turbine with one intermediate stream at 195 psi and an exit stream leaving at 62 psi with no condensate being formed. The first turbine is more efficient due to energy released from the condensation of steam, but it cannot produce as much power as the second turbine. Excess steam may bypass the turbines to the two levels of steam through pressure reducing valves. And then this is a picture, okay, of what is happening. So we have fuel going into the boiler and the boiler supplying, of course, steam to two turbines, turbine 1, turbine 2. So we have steam supplied here at 635 psig, okay, high pressure steam. And then, of course, the turbines produce power. So we can see what is going out here. We have power going out, okay. So all of these pictures trying to explain what is happening here. So we have the boiler feed water 1, boiler feed water 2. So table 2 lists the information about the different levels of steam. Table 3 gives the demand on the system. So to meet electric power demand, electric power must be purchased from another producer. That's where you see a PP, purchasing power. So you purchase power to be able to meet the power demand, okay, with a minimum base of 12,000 kilowatts. If the electric power required to meet the system demand is less than this base, the power that is not used will be charged at a penalty cost. Table 4 gives the cost of fuel for the boiler and additional electric power to operate the utility system. So here, these are the various keys. I1 represents the inlet flow rate from turbine 1. So inlet flow rate of steam to turbine 1, I1 to steam turbine 2, I2 is a variable. Okay. HE1 represents exit flow rate from turbine 1, okay, or turbine I, which will be 1 or 2, to the 195 the psi header, which is the medium pressure steam header. Okay, so H1, H2. Likewise, LE1, LE2. LE1, LE2 represents the exit flow from turbine I to 62. So we have the from the high pressure to the medium pressure steam, HE, and then the LE is from the high pressure to the low pressure steam, okay, which is the 62 psi header. Okay, all in British units. Then C represent the condensate flow from turbine 1. So we have C, which is the condensate flow. Mind you, question says we have condensate generated from turbine 1, but no such condensate from turbine 2. Then PI, which is P1 or P2, okay, represent power generated from turbine 1 and that of 2 from turbine 2. BF1 represents the bypass flow rate, okay, from 63 psi to 195 psi header. So BF1 is a bypass flow, okay, bypass flow. Sorry, it is from 635, not psi, not 63. It's from 635. Then BF2 is also what the bypass flow rate from 195 to 62. So this is from 635 to that. So let's go back up. I'm defining the parameters. So likewise, HPS is the flow rate from 635 psi order, medium pressure steam, LPS pressure steam, PP is the purchase power, EP is the excess power. Okay, excess power. Difference of between purchase power from the base power. So we have table 1 is giving us the maximum generative capacity for turbine 1, turbine 2, minimum load, maximum inlet flow, just giving us all the characteristics that we have for turbine 1 and turbine 2. Just take your time to go through it. I'll also leave a link of this notebook, okay, to this video so that you can download it and follow through on your own and also practice this problem. Actually, this problem is taken from the textbook I made earlier, which is Optimization of Chemical Processes by Edgar Himmelblau and Laston, second edition. Okay, so back to our problem. So this is the steam header data. Okay, we have the various steam header data, the pressure, the temperature, and the enthalpy. Then we have demand on the system. Okay, medium pressure steam, this is the demand, low pressure steam, and electric power. Okay, demand on them. And then these are the constraints. Then we have energy data, fuel costs, purchasing demand penalty, okay, demand penalty, purchase power base, electric power, purchase electric power, the cost. So this is also important. We started by looking at input optimization case problem, looking at over units, but here we're looking at the plant-wise optimization problem. So the following objective function is the cost to operate the system per hour, which is the sum of the steam produced, HPS, power required, and excess power. Because we don't want to, first of all, we are producing power from high pressure steam, and then we're also taking some purchase power, and then we may have excess power. So that forms the basis of our objective function from this problem. Because if we have excess power, we'll pay penalty for it. So we need to optimize the system such that we don't have that waste of excess power. So here we have F equals, and then we passed in the cost of them. Of course, the cost functions are detailed in the fuel cost here. So for the steam, that value times HPS, and then the same thing for PP, purchase power, and then for excess power, the penalty we pay on it. So that is, we want to minimize this. Subject to the following constraints: P1 must be less than this, P2 must be less, greater than or equal to that, and the flow rate. We can see that here detailed in this table. Yes, in this table is detailed here. So that's the constraint that we have on the system. The condensate must be less than or equal to 62,000. It's highlighted here, and the value given in the table. Maximum condensate rate, maximum. Of course, turbine 2 does not have condensate, so we don't have that condition there. So, and then the difference between these must be less than or equal to 30,000. H1 is the steam, I1 is the inlet flow rate of the steam to turbine 1. Okay, the difference between that of turbine 1 and HE1, okay, the outlet must be less than or equal to, I think it's stated in the problem, must be less than or equal to, what do we have there? 132,000. So that's it. You have it in this table here. The maximum internal flow. We don't have that restriction on turbine 2 because we don't have that specification for turbine 2. Okay, we don't have condensates generated from turbine 2. So first, this is on turbine 1. So on turbine 2, we define our constraints as well on turbine 2. We have all of these constraints on turbine 2. When do you know when to use less than or equal to or greater than or equal to? You just go to the problem. When we have maximum, it means we cannot exceed that value. So we have to operate within that bound. When we have minimum, it means we have to go above that value. It's just like using the word at least. Okay? Minimum. At most, that's the maximum. We can also, when it's at most the maximum, it means you have to operate, within that maximum or less than that, and that's less than or equal to. If you have at least, it means you have to operate between that base minimum and above it. So, of course, the next thing we'll do here is to draw material balances. I will not, of course, chemical engineering student, you can draw these material balances around the whole system. Okay, you start from first across the two units. We have HPF1. Of course, this is the the steam. Okay, the steam balance. Okay, HPS1 minus 1 to minus this difference of this is 0. In other words, the sum of all that is going into the two turbines and the bypass must be equal to the steam generated from the boiler. Okay, so this and this, the sum of these three must be equal to this. Likewise, you go ahead and do across the two turbines and the low pressure steam and the medium pressure steam. You still move ahead and do across turbine 1 for condensate, then 2 across turbine 2 when there's no condensate. Then you do across only cutting across the outlet of turbine 1, turbine 2, the flow rate, the bypass 1, bypass 2, and the medium pressure steam. And you do the same thing for the low pressure steam. So it's like we're doing here. Let me go back there. We're doing material balance here on this, doing material balance this. So you draw a system boundary here. For low pressure steam, you draw a system boundary here. For the full system, you draw a system boundary across here. For turbine 1, you draw a system boundary across here. For turbine 2, you draw a system boundary across here. So that's how I generated those respective material balances you see here. And then there's a constraint on the purchase power. So the excess power and the purchase power must be greater than that minimum 12,000. Then we have demand, okay, on the low pressure steam, medium pressure steam, and then demand on power. Power generated from turbine 1, turbine 2, and the purchase power must be greater than or equal to 24,550 kilowatts. It is specified in the table, electric power here. So we move forward, and then the last thing we do is to draw our energy balances. How do we draw our energy balances? Our energy balances will cut across. Remember material balances because various materials living, but for the energy balances, we are going to draw it across the turbines. Okay, because that's what we have. The turbines, we have the heat exchangers where the boiler feed water bypass. So we go back up here. I'll go back up, and then we draw our energy balance across this turbine 1. So that's why I see it cut across steam entering, okay, condensate leaving, steam leaving to low power pressure steam leaving to medium pressure steam. Likewise, we cut across turbine 2. So these two will give us these energy balances here. And for each of the energy balance streams, we already have the enthalpy specified for us. So now, how many variables do we have? All together, we have 16 variables, starting from the high pressure steam flow rate, the purchasing power, the excess power, the power from turbine 1, power from turbine 2, the heat leaving power turbine 1, the condensate leaving turbine 1, the heat steam flowing to turbine 1, turbine 2. And so we list all of these. Now I've taken time to abstract them as x0 the way you should have them in Python, okay, using the indexing 0, x0, x1, x2, x3, down until you get to x15. So we have 16 variables. Once I finish doing this, the next thing we do is to, from SciPy, import, okay, linear programming dot optimize, import linear programming. Then we define C is the coefficient of the cost function for every variables. How many variables do we have in our objective function? Let's go back to the objective function. Where's our objective function? Our objective function contains only what? HPS, PP, and EP. The rest 13 variables will carry coefficient of 0. That's why you see 0, 0, 0, because they're not there. We're only optimizing this. So 0 times that gives you 0. Then the AUB, I think in my last video, I should have mentioned what AUB and BUB represent. Okay, and then A equality and B equality. I think I should have itemized all of these. With that, I will take us straight to SciPy. Let's go to scipy.org so that I'll just use that to explain what it means. So if you go to scipy.optimize.linear programming, okay, just Google search that on your browser, you will see that it takes C, which is the objective function or the cost function. It takes AUB, BUB, A underscore EQ, B underscore EQ. Now, the A underscore UB refers to the coefficients on the left side of the inequality constraints. B underscore UB refers to the values you have on the right side of the inequality constraints. Now, if you have a mix of inequality and equality constraints, then you also have the coefficients of the variables, okay, in all of the inequality equality constraints on the left side of it. You can see it abstracted there. Linear programming solves the problem of the following form. So this is the form. Okay, never mind C transpose X. It doesn't mean, just like abstracting them as vectors, such that AUBX less than equal to BUB, then AEQX less than or equal to BEQ, and then X has a bound between the lower bound and the upper bound, where X is a vector of the decision variables. C, BUB, BEQ, L, and U are vectors, but AUB and AEB are matrices. Either you call them matrices or you refer to them as array. So this represents the inequality constraint matrix, okay, which specifies the coefficients of a linear inequality constraint on X. BUB is inequality constraint vector. Each element represents an upper bound on the corresponding value of AUB, okay, um, multiplied by X, which is the dot products, okay, or scalar products. The same thing with AEQ, it is the equality constraint matrix, okay, and then the same thing with BAB, okay. So A underscore UB stands for the inequality constraint matrix. Let's go back to our problem, and A underscore EQ stands for the equality constraint. So what I did there was to abstract all my inequality. These are all inequality constraints. The material balances all form equality constraints. The demands here form inequality constraints. The energy balances form equality constraints. So I simply made the demands, which are inequality constraints, with the turbine 1 and turbine 2 constraints. They are all inequality constraints. So I lumped them up together and I abstracted, got the matrix as this way, following these variables, the parameters I've listed there. It's quite tedious, but that's the first thing you need to do. Once you have abstracted that and then abstract the BUB on this side, the problem is was half solved. Now notice something here. I need to draw your attention to this. We have a mix of less than or equal to, greater than or equal to. Now, in the problem defined here, it is presented this way. It has to be less than or equal to. Now, where you have the constraint being greater than or equal to, what you simply do is to multiply um, both sides, okay, by minus. If you multiply by minus, it reverses that inequality constraint. We learned that in our linear algebra, okay, mathematics. So it's like minus p, multiply this minus, this sign, this inequality changes to, so you do that to this, do that to this, do that to this. By doing that, of course, the coefficient becomes minus, and that's why you can find -1 in these coefficients, okay, of the matrix. And then you find negative also in the BUB. Now, likewise, lump the material balance and the energy balance together. Here you don't need to, it's just equality constraint. What you have across are all zeros, and that's why you can find the B equal to all zeros. And then the coefficients of the variables before the equality sign, I lump all of them up. You can see that and put that in this matrix. Now, likewise, if you read through the problem, you notice that in some of the variables have bounds. I have 25 to 6250. Also, I have 3000 to 9000. Let's see, 9000, 6250. Let's go back to the table. I'm trying to explain what I've done there so that it becomes easy for you to walk through as well when you're doing. So now that's it. You can see the minimum and the maximum generative capacity. So that's the bound on the turbine 1, on turbine 2, 3000 and 9000. So that's where these bounds come from. But for others where you have no bound, mind you, the non-negativity bounds all apply here. For all the variables, they have to be non-negative. So that's why you have these two bounds, while others are 0 and none. You can either use none or use NP, non-pi dot infinity. So having done this, then we'll call the solution to be, of course, we'll call linear programming passing C, passing our AUB, passing BUB, passing A underscore equality, passing, and then passing the bounds and the method. Let's go back to scipy.optimize.linear programming. You can see the method specified there as high. That's highest. That's the default method. But you have other methods that you can use. You have highest DS, you have highest IPM, you have interior points. That's the legacy one. You have the revised simplex, you have simplex legacy. All of these are supported in SciPy. Okay, so if you don't have the upper bound, you can use none. Okay, if you have, you can see to mean all bounds, all variables are to be real. Okay, but to indicate a non-negativity bounds, we have to use 0 and none. Otherwise, you're passing the minimum and the maximum. So having done all of these, we just simply run the cell and like 1 second, scipy.optimize. Okay, it's there, the solution is there. I can call the solution. You can see it returns, this is my optimal function, the optimal values of x1, x2, x3, and it gives you additional information here. It says optimization terminated successfully, and I've gotten optimal results. It gives you the lower residual, both on the upper and the lower bound, on the inequality constraint and on the equality constraint as well. But I don't need all of this information. Now I've come here to abstract my parameters as I've itemized them here. I want to run a loop through the solution to print out the value. So I say print optimal solution. And then for parameter and value in zip, I zip these parameters, which is a list of my variables, and the solution.x. And I will just print parameter equals to this value. And then, of course, also print the optimal cost per hour solution.function. If I run this cell, it gives us the optimal solution. So these are the optimal solution, the amount of high pressure steam, how much power you should purchase, excess power generated, power from turbine 1, steam from turbine 1, the condensate by 1, and all the way through. And the optimal, you can see the low pressure steam, there's no low pressure steam supplied from turbine 1. Likewise, there's no bypass flow rate to 1 and 2. And that will give me, of course, I'll have a low medium pressure steam of this, and I'll have an optimal cost of operating the plant per hour to be $1,270. I hope you understand this problem that we have solved. It's quite a complex problem. Solving them by hand using the simplest method will be very, very tedious. But you can see how Python and using the respective library SciPy, we have been able to solve this problem in a jiffy. Like this video, share this video so that others can benefit from this as well. And if you're new to my channel, just watching this video, please do well to subscribe to my YouTube channel as a way to encourage me to keep pushing out more valuable content. Stay on to my channel and you'll see more videos on this series. The next I'll be discussing will be on curve fitting. Okay, and on curve fitting, I'll take various problems just like I did under optimization. I will see you in my next video.